substations. If you remember how we did the, I can't even see you, Phil, now with all this hardware, man. Next to oh my God. Is that intentional here or what? Okay, if you guys remember what we did with the residential and the commercial project, we brought the service conductor from a transformer set outside the building into the panel inside the building. And from that service entrance panel, we send all these feeders and branch circuits directly to the equipment, right? That's what we did for the commercial industrial building. Now, if you have a hospital, a sport arena, now remember, we're elevating the level now. Hospitals, sport arenas, major industrial building. There's a better way of doing the system. So what they do, like we did Ganda building for Mayo Clinic with LB back, that's exactly what you're looking at, is exactly what we installed. What they do, guys, is really easy. You bring the feed, they bring either from the top or the bottom. What we did is we brought it from the top. So we bring the high voltage from the top, so that would be 13.8 kilovolt. So we brought the high voltage from the bottom, from the top, and then we came through the transformer. We broke it. I'm just going to show these. And we came over here. Here's my transformer. From the transformer, we put a circuit breaker. From the circuit breaker, we put other circuit breakers to distribute the power. So why would I do a system like this? Very expensive. If you put the distribution transformer, guys, as well as the high voltage section and the low voltage section in one big fat box with with the divider between them, they call this is unit substation. Unit substation. With every time you hear in an engineering firm or contractor, you hear them talk about unit substation, that's exactly what they mean. They mean a high voltage section with a transformer. Let's just suppose that this section, this transformer was 1500 kVA. And this voltage, let's just say, for the heck of it, 2000 amp. And the voltage here is 480/277 volt. Can you guys see how we brought the high voltage into the line side of a transformer? Out of the line side, out of the transformer load side or secondary side, we went into a panel. So in the past, when we did residential and commercial, this part here, the high voltage was part of the utility. The transformer was owned and operated by utilities, and the only thing we worried about is the low voltage section. So as you go, this will be called high voltage section. This is, of course, a transformer. And what do you guys think this would be? Low voltage section. Any question about the high voltage section, low voltage section, and the transformer that make the substation? Any question about that? Let's start with the point. Number one, they call it Pophead. Hold on, I'm doing it. I'm saying it right. The Pophead here, which is right in this point, guys. This is when you bring a high voltage cable 13.8, it comes as a cable, right? At the top coming as a cable, and then you need to bring it into, it's like a termination box. You need to terminate it right in here to get into all these fuses. That device, the Pophead, take the cable and split it into buses and tie it to the fuses. Right in here, tie it to the fuses. There's a nicer picture of it. Who cares? It takes a cable that's coming from overhead and split it. Okay, one point, split it into 1, 2, 3 buses, tie it to the fuses because you have 3 phase. Number two, if you guys, every time you have high voltage, you have something called surge arresters. Can you guys see the surge arresters here, or lightning arresters? These will look at any lightning that hit the transmission line, and instead of burning your equipment, it suck it directly. It shunts the phases to the ground. It take all these high voltage directly to the ground. Who cares? It will protect your switchgear from blowing up because of lightning or transient in your system. Look what they put them right here as you enter the switchgear. Moving down to fuses. Every time we need to fuse, guys. So I have my fuses right in here. Fuse. Can you guys see that? These are my fuses, high voltage fuses to protect the transformer. On the primary side, we will be sizing these guys, and we sized them before. So I put my fuses, and then they bus them. They don't use cable between these two. They bus them with copper. They bus the load side of the fuse directly into the transformer. Most likely it's dry type transformer. meaning there is no oil inside it. Most of these are dry type transformer, they're just coils. Here's phase A, phase B, phase C, transformers come out of them. Out of the transformer, they also bus it. When they say bus it, there's no cables. They're all bussed together with copper into another section that's for low voltage. They put an overcurrent protection device here to protect this low voltage panel, right? And then from the low voltage panel, you can go feed your air handling unit, chiller, rooftop units, all your equipment. Okay, so we have three. We have number 4. I don't know if you guys can see. Look what they put the grounding bar. They put a grounding bar right across the whole area here. They put a grounding bar right across the whole area where you can ground the shield. If you have a shielded cable, you ground the shield with the cable. You ground the transformer. You ground the transformer here. And also, you ground if the transformer is grounded, you don't have to ground it again. So they ground the transformer right into this called grounding bus bar. We know what the transformer is. That's my transformer. And you go to tabs. Can you guys see where's tabs? Tabs should be number 6 right in here. Okay, here you go. Can you guys see these? These are my tabs. We'll talk about tabs later on. Very important tabs. Tabs is supposed to get you, if there's a low voltage on the transmission line or distribution line, you can adjust the tabs to adhere to the low voltage system. So really nice. If I am to get you one little thing that's about low volt, the tabs here, it always guarantees you. Can you always guarantee you 480 at this system? It's supposed, no matter what the voltage fluctuates on this side, the tabs always guarantee you a close to 480 at the other side. That's why we have the tabs. Okay? Because we don't care what the voltage in this side is. We're not tying anything to it. We care about this side, always guarantee us 480. So this is my tabs. Load side terminals. We talked about load side terminals. Number 7 here, my load side terminals. And secondary bus is number 8. Where's number 8? Number 8 is, here's my secondary bus right in here. And we have number 9 is a neutral. Where's my neutral? Neutral is sitting right at the top here. My neutral is sitting right at the top. And remember, the neutral will be tied to the ground at the transformer, or at most of the time it will be tied right at the transformer. Any question, guys? Any comments? This is what consists, what we call a unit substation. Where would you use this unit substation? Hospitals, sport arenas, major buildings. I used it myself for a project for Mayo Clinic, Gunner Building. We brought 13.8, believe it or not, 13,800 from the first floor, and we took them to, I can't remember, 13th floor. That was the electrical equipment. So that's cable coming from here underground all the way to the 13th floor. We have a section with a fuse for the high voltage and a transformer. And this side was 480. One substation was 480, 277. The other substation was 28, 120. Very common in major, but that was 32-story building. And at the 13th floor, what they do, and then you put it at the 13th floor and you go down and you feed all your equipment. So you take the substation, put it at 13th floor, and you come down and you feed from 13th floor down 13, 12, 11, and so forth. Go feed down almost 5, 6 floors out of this substation. Any question, guys, about this substation? Cool? So that's, we didn't do a substation. In this project, guys, I want to remind you, if this transformer is owned and operated by the utility, you cannot have a substation. The good stuff about, like in Mayo, they own their high voltage section. They own the high voltage section here. You own the high voltage section. If you own high voltage section, this becomes a lot, very, very important to do it this way. If the utility have the low voltage section, most likely your transformer will be outside and your high voltage section will be under Excel or utility jurisdiction, so you don't have to do that. Or it doesn't make sense to do it. Any question about this substation? Any question about this substation? What we did for the substation, another example of substation that we did, guys, is you can have another example where you can bring voltage. Take this. I bring a transformer here. This is right in here. Here's my transformer. Out of the transformer here to the panel. Here's another application. This is 208, 208/120. This side is actually 480 volt. This is another low voltage substation, right? You have a 480 on this side, just one, a transformer, and a 208 on the other side. That doesn't have high voltage, as in like 13.8. So you bring 480, fused at 480, you fuse the transformer. This is typical when you could do data centers, power distribution units. Very typical to this. Typical for power distribution, they call them power distribution units. Typical, similar to this, very similar, where you have one section for 480 and one section for a transformer, the other section is 208. Any comments, any questions? So that's what I wanted to show here about the substation. The rest of them, guys, here's what they call it, Pophead. This is high voltage. You bring cables from the top, phase A. Oops, let's use left to right. He is coming from, this is phase A, phase B, phase C. And these are spaced, most of these guys spaced like 2 feet away from each other. And they're all coming from a power line here, right? Each one of them is landing on one side of the power line, right? You can imagine that. Coming to your building, then we're going to bring them they are 2 feet away from each other, right? We're going to group them together, tie them at the end here, and we're going to group them inside, keep the separation between them, and bring them into right here, right? And at the same time, keep the separation. So what they do with the smart event, Chad, they have some fill plugs. You can fill them, put the cables inside, fill it. Porcelain insulators, they have to have insulators so the voltage doesn't jump to the ground. And then from over here, they tie them to the phase A, phase B, phase A, phase B, and phase C. So it's like a connection point where it takes cables like this coming from the top into closer together, put them closer together, and dump them into a switchgear. How else would you do it? So keep just this in mind with the symbol that they use for it. It's a termination point for high voltage. If you don't use with high voltage, probably you wouldn't deal with it that much. Lightning arresters. Lightning arresters, guys, this is supposed to, what they do is they take phase A here, here's phase A, and they take this to the ground, literally, and spark gap, and they have the gap sitting right in here, and literally sitting like this. So here's what they do. If there's a lightning, look at this. If the voltage here is nice and sinusoidal, right? No problem. The minute that this voltage goes to the Lord and comes down to the devil and up back again to the Lord, what's happening here? Right? And then it goes back again smooth. Can you guys see this is called the transient? You got hit by lightning here. In this section, you got hit by lightning, right? And then it goes back normal. The lightning is over. Just that section here, just that section from here to here, because it's high voltage and because of the gap between the phase and the ground, the voltage, because it's so high, it will jump. So the voltage will jump here, and it will take all this voltage down to Earth, to Mother Earth. Who cares? Your equipment will burn. What makes this close? It's really a gap. But because of the high voltage, the gap is made centered to jump if the voltage goes higher than this voltage, higher than the normal voltage. And they have a rating for it. So if it goes higher, because of lightning or switching transient, it just closes, shunt phase A to the ground, and the same thing phase B and phase C to the ground. Momentarily, for milliseconds, guys. Okay? So who cares? Now you protect your equipment from damaging. Your equipment is protected. Any comments, any questions? Lightning arresters?
So where would that be located?
In the switchgear that we had, they put them indoor. They put them inside the switchgear, right here. In the switchgear that we have right here. See them? They put them phase A, phase B, phase C. If it's for the transmission line, you see them all the way sitting right into the cable. You see it something like this. You see them all the way. If you look at the power lines, as you go from the power line into a cable, always as you go through a cable, you have one. Or transformer, you have one right before you get into the transformer to protect the cable or the transformer. Good point. But in a unit substation, they will be inside the unit. Okay. The The second thing that this chapter, guys, talks about is calculating the impedance of the transformer. Transformers have something called impedance. Impedance is important because it decides how much short circuit can come into my building. So if you guys look at this one, the way they measure the impedance, obviously this is just experimental. The way they measure the impedance of a transformer, you take, if it's a three-phase, take one winding of the three-phase, just one phase, right? Here's the secondary. Suppose that this secondary, let's just say the primary was 480, here's the voltage, and the secondary was 208. Okay? All right, so the secondary. What they do, guys, is they go shunt, take a wire to one winding and connect the wire together, right? They just shunt it. Can you guys see that? How it's shunted? They shunt it. And they have a voltage, adjustable voltage. They start increasing the voltage until you get the secondary current. So suppose that the secondary current here was 30 amps. Suppose the secondary current was 30 amps. You know how to find the secondary current of a transformer. You take the voltage divided by the secondary voltage. The kVA divided by the secondary voltage. So you have a kVA divided by 1.73 times V secondary, right? From this, I came up with 30 amps. What they do is they shunt it, they connect it, they start adjusting the voltage up until the meter reads 30 amps. They stop. Does that make sense? They shunt this, they take a piece of wire and connect the phase A to phase B, for example, or phase A to the neutral in this case. And they start adjusting, and they put voltmeter here, they put a voltage source right here, and they start measuring, adjust until they get the amps, 30 amps. Suppose this read at 30 amps, let's just say it read, to make it easy, 100 volt. At 100 volt, I received the 30 amps, you stop. To find the impedance, very easy. To find the impedance percentage, or percentage of the impedance, you take the 30 amps divided by the voltage 100, and that will get you what? 3%? 30%. That's too much. Let's just say that you got to make it. Let's just say you got 1,000 volts here. So divided by 1,000, and that will get you 3%. I'm looking for 3%. I will adjust the numbers. So you get 3%. That's how you do it. I don't want to spend too much time on it, guys, but that's the method. Really straightforward, no gimmicks, nothing. You take the voltage that you get, that gives you the secondary current, and you divide the secondary current by the voltage, and you get the impedance of that transformer. Most of the time, this is in the field, this is for troubleshooting, guys. We don't do that. For us designers, the Z will be planted right into the switchgear, right in the face of that transformer. Right into the face of that transformer. Okay, so that's, then, if you guys look over here, I have 450 right here. 450 is we're going to be doing transformer sizing. So when we size the transformer, we need to size a primary protection and secondary protection. It's coming. I'm not going to do the calculation for it. We will go to Article 450, NEC, and do the calculation how to size a primary and secondary fuse for the transformer. So it's coming on our calculation class. So don't sweat it too hard. Again, we're going to size it, the primary and the secondary. We'll go through the whole space. Okay, one thing, guys, I want to emphasize. Look at this. This is the taps. The taps is a new concept for the most part for all of us. What they do is most of the transformers, they have at least primary taps. A lot of them also have a primary and secondary taps. So take this. So what is the tab and why do we use it? The tab, the most important thing, guys, about the tabs are piece of white connection point inside the transformer. Connection point inside the transformer. So the goal, so let's just say what's the voltage here, primary, we don't have the secondary, it's a Y delta. Suppose that the voltage here is 480. Your your goal, mostly utility guys, we really rarely, if we ever get involved in the building side, the utilities goal is to get you right at the service a 480. Now, what happened if your neighbor start welding 3 miles away from you and you and him are fit from the same transmission line? The voltage goes down. The higher the amps, the lower the voltage. So imagine on the transmission line, if you guys can see that transmission line coming in here, phase A, phase B, and phase C, because my neighbor here at this side start welding in his factory, the voltage went down. So if the voltage, so this, it give you the following connection. If you have the voltage, the normal, this connection right here, I hope I can catch it, right in here, this is the normal connection. That's the normal voltage. Where is it? Right here. Can you guys see that normal voltage? 4160. The system is rated for 4160. That's a nominal voltage. Now what happened if your guy start welding down there? The voltage is going to dip down. If it dips down, let's just say that guy starts welding and the voltage dipped down from 4160 into the worst, into this voltage right here, to 339.52, right? So what the utilities can do is they can grab this connection right here. Can you see it? And tie it right into this connection. By doing that, guys, it guarantees you always 480. Because what happens if the voltage on the primary dips, the voltage in secondary will dip down, and you might end up here with a voltage of 450, which not good.
How is that? Are those common or are they moved from the floor?
Good point. There are two types of these. There's one, the one that affects us is actually stationary, and they do it twice or 3 times a year, mostly twice. One in the summer and one in the winter, because the loads, guys, fluctuate dramatically between summer and winter because of heating and cooling, right? So in the winter, a lot of utilities, in the summer we peak in Minnesota. In the summer, they come and they adjust this one to go to the exactly where it showed it here, because the transmission line will, in the summer, will be overloaded. In the winter, if they keep it where it is right now, you're going to have high voltage. You're going to end up with 500 volt here. That's bad news too. High voltage, low voltage, bad news. So what they do, in the summer they sit it here, and they come back in the winter, see, and they sit it exactly where it used to be.
So they move it.
They move it, physically, mechanically move it. That's one type. Physically, mechanically go to the top of the transformer, and the utilities will adjust it. That's one type. The other type that the utilities use, guys, they call it auto voltage changer, voltage tap changer. And on these, who's going to be doing it on the transmission lines? Nobody's going to be doing it. What they do, they on the transmission line, they're smart enough to have an auto device that tracks the voltage, and there's a motor that adjusts these as the voltage goes up and down, adjusts the connection on the transformers. We rarely, if ever, do that one on the building side. On the transmission and distribution side, utility type, they use it all the time. Auto voltage tab changer. We're not going to go that one. This is what we are showing here is physically, mechanically, somebody have to go take that connection from here, tie it to the other one. Now what happens if the voltage goes higher? Now that welder guy stopped welding. I'm just showing that one. And the voltage went high, very high. The voltage went, as a matter of fact, as high as this, right here. They went 4, 3, 6, very high to this point. If you put this voltage on there, on the system, you're going to get a higher voltage system, right? High voltage is as bad as low voltage. So what the smarter than Chad do, they come take this point here and they tie it here. They take that connection and they tie it there. By doing it this way, long story short, you always guarantee it what? 480.
And that facility is the reference point.
Yes, yeah. 4160 is your point of connection. Most of the transformer come with 4 points. They call them plus or minus 2.5%, and this is 0.1 or plus or minus 5%. Okay, so if you look at the first one, this point here, this will be the 2. This point will be the 5, and this point will be the 5. This point will be the 2.5. This will be the 2.5. Plus 2.5% or minus 2.5%. Does that make sense? So that will give you 4 taps, right? 4 taps. And oh, by the way, they do it in every phase. They do it on every phase. It's a big deal, guys. Tab changing and tab changers, big deal in the high voltage section. They also have a tab change sometimes here. You can tab change here on the secondary side. Do the same thing. You can, between the secondary and the primary, you can get a good voltage. If you like Dunwoody guys, they come here to a transformer. If we're having a low voltage all the time because our load changes, you know what they do? One of the problem solving to go to the transformer that's feeding Dunwoody and change the tab. If we change the tab, put it to, if we're having a low voltage here, they go measure the voltage on the transmission line. The low voltage is low too. So what do? They adjust the voltage tab, and you're good to go. That's a way for the utility to get you a good nominal voltage. Can I get you guys to give me a thumbs up that we understand what tabs do? This is very, very important concept. Understand, if you're a project engineer and you walk into a building, you have a low voltage. What would you do? And you measure right at the surface and you have a low voltage. The first thing should come to your mind, maybe I should contact the utility and see if they can adjust the tabs on the primary of the transformer that's feeding this building. Here's a hint for you, right? That's one hint. So keep this in mind, tabs on the primary of the transformer. So that's a new concept for the tabs. And we will do calculation on the tabs, really not a whole lot. If you guys can see, I don't know if you notice that this value, you know what this value is? This is not rocket science. This is taking 1.05 and multiplying it by 4160. That's it. If you take 5%, multiply it by 416, you get this value. And this is also not rocket science at all. If you take 5% out of 100% is what? This is 0.95 because these are minus 5%. And multiplied it by the 4160. And to make things, I want to do one of them here. Here's another one. This one is actually
1.45 times 416.
am I doing it the higher voltage? Yes. These are, I'm switching it. This one should be, thank you. This should be 1.05, and this one should be the 0.95, right? Thank you. 0.95. Speaking with the devil here, this one then it's going to be, because we're going lower, so this would be 0.9. What's 2.5 minus 100? That will be 0.975, right? 0.975 plus 0.25 give you, would that give you 100%? Multiplied by 4160, and if you take that baby here, that will get you 1.25 multiplied by 4160. Done. This is how they came up with these numbers. Plus or minus 2.5%, plus and minus 5%. But the concept is always get you a transformer. This is a really nice way, guys, of showing you inside the substation. Can you see, Chris, how they bus them? Look at the buses, copper buses. They're busing out of the transformer. No cables, nothing. They're all copper or aluminum buses. Obviously, we don't size this. It's sized by the manufacturers of the unit sub. Oh, the tabs. I want to see the tabs. Can you guys see where the tabs are right here? Where it changes, they can go right inside the substation and change the tabs. And it will say 2.5%, 5% above, below. So it's really not rocket science. Take this wire from here. It was connected here. You take it from here, go here, or go here, or go here, from one side. That's all. On every phase, though. On every phase. So that's my tab changer. On if the system is ungrounded system, guys, most of the system that you're going to deal with is a grounded system, meaning the neutral is tied to the ground. That's a grounded system. If your system is ungrounded, they allow you to use an ungrounded system for process control. You have an assembly line that you take a cow from this side, canned beef from the other side. That's the system. Steel from this side, a car from the other side or a truck from the other side, that's a process. They allow you to use ungrounded system with this. Meaning, if you have a short circuit on ground, one phase, that's the beauty of ungrounded system. You have the first hit on phase A, you're still standing. Anyway, if you have an ungrounded system, you're required by code to monitor the ground fault. Here's a method of monitoring the ground fault. That's the poor man or woman method. The poor man or woman method is you tie these to the ground, and you can see how these are all tied to the ground from one side. From the other side, they're tied to the phase, each phase. Take this. If I have a ground fault right here, now phase, let's just say phase A, phase B, phase C. Phase C went to the ground because of a ground fault, right? Phase C went to the ground. All these will be, most of the time these will be lit. This lamp will dim or go dead, right? Because the voltage between phase C and the ground now came to a halt, 0. So this is a visual indicator. A lamp, right above the lamp, there's a label that says, oh, by the way, ground fault in phase A. Does that make sense, guys? If the voltage is to go on phase, let's say in phase A here, it was in phase C before, then this will go on, and where's phase A? Phase A will dim. Now this is a visual indication that I have a ground fault in phase A. Who cares? You can put your maintenance guys to say, oh, by the way, when phase A, nothing will happen. Your system is up and running. You're running on a grounded fault. Ungrounded system, you ground one phase, nothing will happen. But you get the second ground phase on a second ground on the second phase, you're down. So you put on your schedule for maintenance. You ask your maintenance electrician when everybody goes home in the middle of the night when we're shut down, go track this ground fault and fix it. Any question, guys, about ungrounded system? Ungrounded system where by the way, if you look at this is coming from here, from a delta. Here's a typical ungrounded system. That's a delta here, right? This is phase A, phase B, and there you go, and this will be phase C, right? How do I know that there's a ground fault in a delta? It's an ungrounded system. You put an indication. There's also ground fault, electronic ground fault protection, guys, and so forth that you can put on it. But this is the visual indication that you have a ground fault system. Metering, high voltage meters and low voltage meters. This is a CT, guys, that you can do on a high voltage system without getting into too much details. The most important thing I want to mention is you're going to have watt-hour meter. Can you guys see that? VAR meter. Why do you think we have watt meter and VAR meter? Because watt will give us how much we consume, and VAR will give us the power factor. If you look at these guys, CTs, these are how they do them in high voltage. They have CTs, a donut. Looks like a donut, and you put the phase right through it. CTs, they also use the PTs. They call the PTs. Here's my PT. This is the open delta, don't worry about that one. 40 to 1. That voltage will give you 120 on this side. 120 volt on this side from a 4160 on the other side. This voltage, if the current here is down here 2000 amp, the current that comes out of that baby is 5 amps. Why 5 amps? Because I can't let a 2000 amp go through a meter and expect this meter to handle it. So that's what current transformers, we have calculation about current transformers coming. Current transformers are supposed to take a very high amp, reduce it to a very low measurable amp. In America, in the US, it's almost always 5%. In other parts of the world, they use 1 amp, 5 amp versus 1 amp. Okay, so this is what I want to mention about this one. If you guys look at, so these are the maximum for these measurements. If you look at this, remember, I think we did this one in the commercial too. There's meter A, meter B. When meter B reads 1/2 of meter A, meter B reads 1/2 of meter A, this means the power factor is 90 and higher. We're good. Now, when meter B reads less than 1/2 of meter A, the power factor is less than 90. So meter B less than half of the meter A. So this means the power factor is less than 90. And when meter B reads more than 1/2 of meter A, the power factor is below 90, and the penalty rate, so below 90, who cares? This is a keyword. Penalty rate is charged by the power utility. If they're the same, if the meter B reads less than 1/2 or equal, this should be equal, then the power factor of 90, this is where about 90. If B equals half of A, the power factor is 90. So anyway, so that's a visual indication, guys, of how the power factor is rated. I care less too much about the whole reading, because if you guys look at the meters, they have a power factor. Almost all digital meter right now have a power factor right in the middle of it. You can scroll and it would tell you at every moment what your power factor is. This is just for the old days when you have to have 2 meters, these dial ones, and so you need to compare them visually and see what your power factor is. Almost always now, in this day and age, all the meters that are installed in the building are digital meter that give you the power, the VAR, the power factor, the voltage, the frequency, the harmonics. So it becomes not a big deal. But please pay attention to these little things here in terms of how to read a meter in the high voltage or low voltage section. High voltage or low voltage section. Any question, guys, about this? That's basically the most important thing in this chapter. Any question? Chris, did we miss anything? I don't want to. Any question? We'll talk about the CTs and the PTs in terms of calculation. Any question, guys? The most important thing is understanding what a substation is. Really is. That's the whole important. A grounded and ungrounded system, we'll talk about it. We have a lot of calculation that we're going to do about grounding electrode and all this good stuff. Any question? Phil, my friend? No? So that's basically what I have for you. I don't know if we talked about the sizing. We'll talk about the sizing, guys. Pophead, we talked about these. Fuses, when we size fuses, continuous current and voltage and frequency. The most important thing when you size a fuse, which you're going to see, does it match the voltage and does it match the current? Frequency, almost always 60 hertz in the US. Coordination, we'll talk about these. Minimum transformer. A couple of gauges. This is just primary, secondary, how to calculate the impedance, how to size them. Coordination. We will talk about the coordination, guys, the overcomputation coordination in details, because we have a software that we use. You'll see how when we show all these curves, how the curves are going to coordinate with the inrush of the transformer. So tabs, talked about the tabs. The most important thing I'm going to emphasize is the 2.5% above, 2.5% below, and the 5% above, 5% below. Protection, grounding, the neutral, and the measurement. Okay, any comments, any questions? I don't think we missed any. That can't wait. All the calculation, guys, about the transformers, we will do calculation separate. I separate the calculation. My goal from this chapter is to understand what a substation is, what are the major components of a substation, how do we measure the impedance of a transformer, short the secondary, inject voltage on the primary, adjust it to get the current of the secondary divided by the voltage on the primary that achieved that current. Ungrounded system, you measure it with these, we have meters right now to measure it, but with the lights, if you have a ground fault on one phase, the light will dim, you have a ground fault in that phase. CTs and PTs, we will do a calculation about CTs and PTs. Any comments, any questions? Any questions, my friends? Okay, let me see what we can do here.
But unit substations are generally